Good morning, everyone. It's Miss Manili. Sorry I'm not here today, but I did want to go over the warm-up and some of the problems from your homework last night just to make sure that if you had any questions, they get answered before you begin the review today. Before I do the warm-up, though, let's just review the rules for probability that we've discussed so far. The first rule would be our general addition rule, which basically says if I want to find the probability of A or B, and that's the union, then I'm going to find the probability of A. I'm going to add that to the probability of B. And if the two events are not disjoint, that means if they overlap, then I also have to subtract away the overlap, which would be A and B. And that would be what we call an intersection. On a Venn diagram, so if I were to draw a Venn diagram showing the events A and B, the union, I do this with a highlighter, the union is going to be all of that, whatever falls in either of those circles, and that will include the overlap. And if you think about what this formula means, if I were to add the probability of A, I'd be adding this entire area. If I add that to the probability of B, I'd be adding this whole area. The reason that we have to subtract away the intersection is because that area gets added twice. So this is what we call the general addition rule. We also have the general multiplication rule, A and B. So OR means add, and means multiply. This is an intersection, so sometimes you'll see that symbol. The probability of A and B is the same thing as the probability of both events occurring. So that would be the probability that A occurs times the probability that B occurs given that A occurred. So that's the general rule. If the two events are independent, then it becomes the probability of A times the probability of B, because the probability of B wouldn't change given the value of A, or given the probability of A. And when we're looking at a Venn diagram, and we're looking at A and B, again, I mean, I kind of did this up in the graph above. My and, that intersection, is going to be the overlap. I could also rewrite my formula. This formula can actually be rewritten, so now you have a conditional probability rule that says the probability of A given B, so remember that's my given information, would be the probability of both A and B divided by the probability of the given, which in this case would be B. Now what I find is that a lot of students have a tendency to go like this, to say, okay, well the probability of A and B is the probability of A times the probability of B divided by the probability of B, and then they always cancel. You can only do that if the two events are independent. Otherwise, we wouldn't have this general rule, and this is a really common mistake. So this only happens if A and B are independent. So don't think that you can always just cancel every time you see that probability of A and B. Okay, so let's go back to the warm-up. The two-way table is probably the easiest way to answer a lot of these probability questions. So if you're given a two-way table, the conditional probabilities are easiest to see here. So it says a psychologist interested in right-handedness versus left-handedness and in IQ scores collected the following data from a random sample of 2,000 high school students. So you're given the two-way table. It says, what is the probability that a student from this group has a high IQ? Notice that we're talking about the whole group, from this group. This is not a conditional probability. This is just a basic, what is the probability that someone has a high IQ? If you want to use a shorthand notation, if you want to use letters or variables to represent each of the events, that's fine, but you need to define them. So if I want to use the letter H to represent a high IQ, I need to make sure that I'm defining my event. So this would be normal. I could say this is right, or R, and this is L, and then I can use variables to represent these events. Okay, so the probability of having a high IQ, for my table it's pretty obvious. I want to look at everybody that has a high IQ, which is this group right here, and there are 200 of them, so it's going to be 200 out of the total in my group, which is 2,000. And 200 divided by 2,000 is 10%. All right, in letter B, it says, what is the probability that a student from this group has a high IQ given that she is left-handed? So we're still talking about the group, but notice that we're given some information. we're told that the student is left-handed. So if I already know that the student is left-handed, I'm no longer going to be dividing by the whole group. I am only looking at the group of students who are left-handed. So when I express this as a probability in notation, I'm going to have the probability. I'm still looking for the probability that the person has a high IQ, but I also have to include my given information. And the given information always comes behind that vertical line. So I'm looking at the probability of choosing someone with a high IQ if I already know the person is left-handed. From the 2A table, I'm no longer dividing by the whole group of 2,000. I'm only dividing by the people that write with their left hand, and there are 100 of them. And of that 100, I want to now look at how many have a high IQ, and there's 10. And 10 out of 100 is still 10%. And so in letter C, it says, what can be said about the two events, high IQ and left-handed? Well, notice that the probability of choosing someone with a high IQ didn't change when I knew that the person was left-handed. That tells me that the two events are independent, but you have to write it out. So what we can say is, since the probability of having a high IQ, given that the person is left-handed, is equivalent to the probability of selecting someone with a high IQ, we can say that the two events are independent. So this is another way of showing that two events are independent. You could also show two events are independent using the AND. So if the probability of A the probability of A and B equals the probability of A times the probability of B, we could also show that the events are independent that way as well. Okay, so if you're given a two-way table and you find the probability of A and B, and that's equivalent to the product of the probability of A times the probability of B, then you could also conclude that they're independent. Okay, in number 2, two cards are drawn from a standard 52-card deck. Determine the probability of drawing two aces if the first card is replaced. So if we have replacement, that means we have independence, assuming that we continue to shuffle, because that tells us that the probability of drawing an ace is going to remain the same after every draw. So in terms of notation, I would write it like this: the probability of ace on the first draw and ace on the second draw. So I'd use subscripts to represent the order. And so in terms of defining my event, I'd say A, capital A represents drawing an ace. So because I have independence, remember that rule that we talked about, the probability of A and B. So this rule, the probability of A and B, is going to be the probability of A times the probability of B given A. But we also just showed in number 1, if the two events are independent, then this simply becomes the probability of A times the probability of B. But that's only when they're independent. And so I'm going to use the independent rule here because I'm told that I'm replacing the cards. So I know then that I can rewrite this as the probability of drawing an ace on the first draw times the probability of drawing an ace on the second. Okay, and so if I think about how many aces are in the deck, there's 4 aces in a deck of 52. So on the first draw, that means I have a 4 out of 52 chance of getting an ace. Since I'm putting the ace back in the deck, on my second draw, I also have a 4 in 52 chance of drawing an ace. And I believe that ends up being 1 over 169, or 0.0059. The second question, determine the probability of drawing 2 aces if there is no replacement. So I'm still asking the same question. What is the probability of drawing an ace on the first and an ace on the second draw? But the probability formula is different now. Because I don't have independence, I have to use my general multiplication rule. And it's the probability of getting an ace on my first draw times the probability of getting an ace on my second draw, given that I got an ace the first time. And so, if I think about this formula, still on my first draw, I'm going to have 4 out of 52. But if I don't put that ace back, there's only 3 aces left in the deck for that second draw. And since I didn't put it back, I now have 51 cards left. So it changes that second probability because I don't have that independence. And then this becomes 1 out of 221, which ends up being 0.0045. Okay. You could also draw a tree diagram here if it would help. So if you think about drawing an ace on the first, and this would be not drawing an ace. So drawing an ace on the first draw would be 4 out of 52. This would be 48 out of 52. If I draw an ace and I don't put it back, then the probability of me drawing another ace is now going to be 3 out of 51. I don't know if it's any easier to look at it this way. Oops, that should be a 2. But that would be another way of doing this problem. Okay, and number 3, this is specifically using a tree diagram. It says suppose 60% of students who take the AP statistics exam score a 4 or a 5, 25% score a 3, and the rest score a 1 or a 2. This is not accurate. I'm not sure where these numbers came from, but I think it's just a hypothetical. Suppose further that 95% of those scoring a 4 or a 5 receive college credit, and 50% of those scoring a 3 receive such credit. 4% of those scoring a 1 or a 2 receive credit. We're asked to construct a tree diagram to illustrate the situation. So a tree diagram is best when you've got a sequence of events. And in this case, I'm going to have the score coming first, and then whether or not the student receives college credit is going to come second. Now, even though there's 5 outcomes or 5 values that the score can take on, it looks like we've split it into 3 categories. So we've got either a 4 or a 5, we've got a 3, and we've got a 1 or a 2. And then from there, the student is either going to get credit or no credit. Credit or no credit. Credit or no credit. So then let's go ahead and assign probabilities. I know that 60% of students who take the exam get a 4 or a 5. I know that 25% get a 3, and the rest get a 1 or a 2. So 60 and 25 is going to be 85%. That leaves 15% getting either a 1 or a 2. It says 95% of those scoring a 4 or a 5. So if I make it to a 4 or a 5, 95% will get credit. That means 5% won't. Because remember, each group of branches has to add up to 1. 50% of those scoring a 3 get credit. That means 50% don't. And 4% of those scoring a 1 or a 2 get credit. That means 96% don't. So that's how you would complete your tree diagram. And so since I used the letter C to represent credit, I want to make sure that I define it. C equals credit. And there's several different notations that you can use for C complement. So you could use the not C, C complement, C with a superscript of a C, and you can also use this notation, but this also, where you have like C hat, or C bar, I'm sorry, but because we're also going to use that notation to represent the mean of a random variable, I would suggest not using that notation because it might get confusing later on. Letter B says, for a student who takes the exam, what's the probability of getting credit? What's the probability of getting credit? Well, notice there are 3 paths that we can take. We can get credit after getting a 4 or a 5. We can get credit after getting a 3. And we can get credit with a 1 or a 2. So this is a combination of rules here because I'll write it out. This is like the probability of either getting a 4 or a 5 and credit. That's one way we can do it. Or a 3 and credit. Or a 1 or 2 and credit. Okay, so we have multiple things going on here. I know with and I multiply, with or I add. With the tree diagram, you don't have to write out this line. It's not necessary, but I do want to see the things that you're multiplying together. So this first branch, getting a 4 or a 5 and getting credit, because it's an and, I'd be multiplying 0.6 times 0.95. And remember, this 0.95 is actually a conditional probability. This is the probability of getting credit given that we got a 4 or a 5. So when I'm using the multiplication rule, I'm actually using the general multiplication rule here. Or means I'm going to go ahead and add, because these are all disjoint. There's no overlap, so I don't have to subtract any overlap. The probability of scoring a 3 and getting college credit, which is going to be 0.25 times 0.5. Or this last branch, which would be 0.15 times 0.04. And if you multiply all that together, you should get 0.701, 70% chance of getting credit for the exam. And again, this is not accurate. I'm not sure where these numbers came from. So I'm not saying that it's not accurate. I have no way of confirming if this is true or not. So that would be the probability of getting credit according to this model. In letter C, it says, what is the probability of getting a 3 on the exam and receiving college credit? So make sure you understand what the question is asking. This is an and. What's the probability of getting a 3 and getting college credit? So this is just one path, right? I got a 3 and then I got college credit. So this is simple 0.25 times 0.5, and that's going to be, did I do this right? Yeah, so that's going to be 0.125. And then finally, in letter D, if a student who is chosen at random among those taking the exam receives college credit. So now we're given some information. We're given that they received college credit. What is the probability that he or she received a 3 on the exam? So I'm trying to find the probability of a 3. That's going to come first. The given is what's behind that line. So in this case, normally with a tree diagram, the given information is along the first branch, but that's not what this question is asking. It's saying if I'm given that they've received credit, what's the likelihood that they got a 3? So here's where you absolutely need to apply the formula. This is the probability of both 3 and C divided by the probability of the given, which in this case is C. And these are the two probabilities that we found in parts B and C. So the probability of both we found in part C was 0.125. The probability of the given, or getting credit, is what we found in part B, 0.701. And so when you put all that together, you should get 0.178. Okay, so just know that like on the AP exam or on the test, it may just give you the information and then simply ask this question. You're not going to be prompted to construct a tree diagram. You're not going to be prompted to kind of set the problem up. So you have to kind of recognize what information is given to you, the best way to organize it or illustrate it, and then what formulas you need to use to apply to answer the question. So I'm kind of scaffolding this to make it a little bit easier, but just get used to these types of problems because you may not be given those prompts. Okay, these are the answers to the homework, so if you could also check your homework, I'll go through the problems that I anticipate you might have had a question about. In number 1, this has to do basically with genetics, and you're looking at genes being passed. In order for a seed to be green, both the parents have to contribute a G gene, otherwise it will be yellow. You're told event M represents that the male contributes a G gene, and F represents that the female contributes the G gene, and you want to determine the probability that the seed is green. Well, it says both of the parents have to contribute a G gene, so according to my events, I'm looking for the probability of M and F. You're told in the problem that there's independence, so I know that this formula is what I need to apply, the probability of M times the probability of F. And in both cases, I think we're told that that's 1/2. That's given information. Okay, in number 2, it's very similar. Suppose that 75% of all registered voters in a suburban district are Republicans. So we've got the probability of being a Republican is 75%. The probability of not being a Republican then would be 25%. It says to determine the probability that the first person that we're selecting 2 people independently again. We're told that there's independence. So we're looking for the probability that the first person is Republican and the second person is not. So if you want, you can use subscripts. So because I have independence, I know that I can simply turn that into the probability of choosing a Republican times the probability of choosing someone who's not a Republican. And so based on the probabilities that I jotted down, that's going to be 0.75 times 0.25. Number 3, I think this is a situation that it makes most sense to construct a Venn diagram. So Venn diagram is basically when you're looking at things that are kind of similar that perhaps overlap, where a tree diagram, it's going to be best to illustrate a sequence of events. So Deborah and Matthew are anxiously awaiting word on whether or not they've made partners in a law firm. Deborah guesses that her probability of making a partner is 7% or 70%. So if this is my circle representing Deborah, everything in here has to add up to 70%. Matthew's probability is 50%, so everything in this circle has to add up to 50%. She also guesses that the probability that both she and Matthew make partner is 30%. So you have to subtract the overlap away from each of the other probabilities in order to set this up. And because the whole sample space has to add up to 1, we know that there's going to be 10% out here. So the probability that at least one of them is promoted, this is, I know I was telling you about the at least one types of problems, but this is a little bit different because I only have 2 options, either one or the other doesn't. So at least one is just choosing from 2 things. If I'm looking at a string of 100 Christmas lights and I say what's the probability that at least one doesn't work, then you have to think about either 1 or 2 or 3 or 4 or 5 all the way up to 100, and that's a lot of probabilities to add. But if you're only looking at 2 outcomes and you're wondering at least one of the 2, it's easier simply to use your addition rule here. So I'm looking at the probability that either Deborah or Matt makes partner. And because I'm using my Venn diagram, I can simply add up the probabilities that make up that union, and that should be 90%. If you want to use your probability rule, you can. That would be the probability of Deborah plus the probability of Matt minus the probability of both. And those are the probabilities that you're given in the problem. So 0.7 plus 0.5 minus 0.3 is also going to give you 0.9. So you can do it either way. Please make sure you show me what numbers you're putting together, though, so I understand where they're coming from. Letter C says determine the probability that neither is promoted. So please take note of the 2 different ways that you can express that event. You could also certainly write in the parentheses neither. And that would obviously be this probability out here. Okay. I'm going to let you just go ahead and kind of take a look at numbers 4 and 5. You're given some data or some probabilities about the likelihood that a general can win a battle. So we've got the probability that he can win a large battle is 0.6. The probability that he can win a small one is 0.8. He must either fight 1 large battle or 3 small battles. And we're told in the problem that we have independence. So basically, you need to figure out the probability that he could win all 3 small battles. And the probability would be 0.8 times 0.8 times 0.8 because we have that independence. That probability is lower than the probability of winning a large battle. So he should fight the large battle. Okay, number 5 is one of the ones that's an at least one problem. So let's take a look at that because this is, and actually so is number 6, because this is the one where I don't think we spent a ton of time in class going over this. So number 5, it says an automobile manufacturer buys computer chips from a supplier. The supplier sends a shipment containing 5% defective chips. So we know that. I wrote that. As soon as I read that, I write it down. Each chip is chosen from a shipment, has a probability of 5% of being defective, and each automobile uses 12 chips selected independently. This is important. If this word was not there, or if it was an assumption that we couldn't make, then I would not be able to answer this question. In part A, it says, what's the probability that all chips in the car will work properly? Well, again, that would be like the first one works, and the second one works, and the third one works, and the 12th one works. And because we have independence, I know I can simply multiply the probability that the first one works times the probability of the second one working, etc. And so the probability that any one of them works is 95%. I can simply raise that to the 12th power. Part B, what is the probability that at least 1 in the 12 is defective? So I always write this out. I'm trying to find the probability that at least 1 in 12 is defective. That would be the same as taking the complement, 1 minus the probability that none in 12 is defective. Well, if none of the 12 are defective, that means that all 12 work. So think about the the language and the logic that you have to think through in order to apply the right mathematics. So if none in 12 are defective, that means that all 12 must work. So now I'm looking at 1 minus the probability that they all work, which is the probability I found in part A. And again, like, this is a type of question where you might be given the information and then simply asked the question in part B and not prompted to figure out the probability that all of them work ahead of time. So maybe a one-question problem that you'll need to be able to answer. Number 6 is very similar. It's a diagnostic test. So I'll let you take a look at that. So the probability of at least one false positive in 140, the complement of that would be 1 minus the probability of no false positives in 140. Okay. And then these are the problems out of the book. So number 73, notice I just jotted down the given information so that when I had to find the probability of both, it was very easy just to apply my probability rule. This is just the multiplication rule. Number 75, I did a tree diagram instead. We didn't have independence here. So notice that my probabilities changed. Once you draw the tree diagram, in part B, you're looking at 2 different branches and the possibility of either, so you can add the branches together. 77 and 78, again, these are more tree diagrams. So I listed the given information. Another way to do that would just be to construct a tree diagram, and then you can answer the questions: the probability of paying with a credit card, the probability of using premium given that the person paid with a credit card. And I think that answer actually got cut off. So in part C, it should be 0.1423. Okay. And 78, again, set it up with a tree diagram. And then problems 80 and 89. Okay, so next class we are going to have an AP drill. So in a minute you're going to get the review guide, and I'd like you to please, please, please work together on this, especially since I'm not here. I'm really going to leave it up to those of you that are, getting these problems right to help your classmates understand them. Obviously, I'll be here on Bulldog Block on Thursday morning, but Wednesday we do have advisory because it's scheduling, so all the underclassmen are going to be getting scheduling information. So please work together on the review guide in class. I do expect you to have it finished before next class. I'll answer questions certainly and go over a couple of the problems that I'm sure you might struggle with. And then we will have an AP drill next class. You will not be able to use your notes, but you will have the formulas available to you. You don't have to memorize those. We will have a unit test or a chapter test the following class, which would be, I believe, Monday. Before break, so please be ready for that. I do have a video posted of me going through the problems on the review guide. So if you get stuck and you need a little bit of help, please refer to that. I didn't post the answer key because I'd rather you watch the video to understand how to do the problems than just copy down the answers. So again, I'll be here on Thursday. If anybody has any questions, you can come on back for Bulldog Block.